Hi everyone, Mr. H here. In this video we're going to look at two examples of Young's double slit. The first one says this: calculate the wavelength of monochromatic light that produces a fifth order dark fringe at an angle of 3.8 degrees with a slit separation of 0.042 millimeters. A couple things I want to point out before we get into all the fifth order and everything here. We're not talking about Star Wars, by the way. Monochromatic is a single wavelength of light. We need to have a single wavelength of light for this to work. Otherwise, different wavelengths of light are going to bend at different angles, and they're going to be in different phases as they meet. So that's important in these types of questions. The second thing is that you'll notice how small these slit separation distances actually are. They're 0.042 millimeters, and we need to put that in SI units, which we'll do shortly. So let's deal with this fifth order dark fringe now. If I have the center fringe, so let's assume we've got a screen right here. And that center bright fringe, this is the center bright fringe right there. And so if on each side of that center, I'm going to have a dark followed by a bright, followed by a dark, followed by a bright. I didn't space these out perfectly. Followed by a dark, followed by a bright, dark, bright, etc. The first order is that one. First order dark fringe, second order dark fringe, third order dark fringe, fourth order dark fringe, and finally way out here I have the fifth order dark fringe. And so what that means in terms of the n value here is that n is equal to 5. Now we also know the angle here is 3.8 degrees. Now I did note in the actual lesson that it's often going to be less than 1 degree, but sometimes it's bigger, and that's okay. And in this case we don't actually need to use the approximation because the angle is big enough. The other thing that we know is that d is 0.042 millimeters. Now, if you remember, there are 1,000 millimeters in a meter, so this is 0.000042 meters. 4 zeros. We're moving the decimal place over 3 places, which is the same thing as 4.2 times 10 to the negative 5 meters. So with all this information, we're going, okay, I've got a fifth order dark fringe. I have the d and then the n value. Well, the equation that I could use for this, because it's a dark fringe, remember this is applying to dark fringes, is this. If it was bright fringes that we're talking about, we wouldn't have the minus a half, we just have an n. But because it's dark fringes, we need the minus a half there. So now it's a matter of rearranging for lambda, the wavelength, because that's what we're asked to find. Calculate the wavelength. We're going to go ahead and put 5 minus a half in here. And then we're going to have that equal to d times sine theta. Well, this is going to be 4.5. And then d is 4.2 times 10 to the negative 5 meters. And sine of 3.8 degrees. And so if I divide both sides by 4.5, what I get is lambda is a value of 6.2 times 10 to the negative 7 meters. That is 620 times 10 to the negative 9 meters. The reason I've placed that as 10 to the negative 9 is because that's 620 nanometers. And the visible range of light is somewhere roughly between 400 to 700 nanometers. And so if you don't get a number that's somewhere in there, you're going to be you've done something wrong. If you're talking about visible light, we're going to get always in that range. And so this makes sense. That's a number that we would expect. And so we can conclude, therefore, the wavelength needed, or the wavelength that's shone, therefore the wavelength that's shone is 620 nanometers. Or you could say 6.2 times 10 to the negative 7 meters. So that's the first example. And so if you have a look at the second example and you know how to do it, you can go ahead and try some of the questions that I've assigned you on your own. Otherwise, I'll walk you through the second one now. The second example says this. Two slits are separated by a distance of 0.050 millimeters. So d, 0.050 millimeters. A monochromatic beam of light with a wavelength of 656 nanometers, so 656 times 10 to the negative 9 meters, falls on the slits and produces an interference pattern on a screen that is 2.6 meters from the slits. So here are the slits. Again, this is exaggerated, obviously, because the distance from the screen is much bigger than the much bigger than the distance between the slits. So this is the D value here. This is the L value. And so the L value is told to be 2.6 meters. Calculate the fringe separation at the center of the pattern. In other words, the distance from this fringe to the middle of the next fringe. So from here to here. That is delta Y. And so with that information, we're just trying to figure that out. And in fact, the distance of the fringe separation at the center is going to be the same as the fringe separation everywhere else. It'll just be easier to see at the center because it's brighter. And so we're able in this case to use this equation, which says that lambda is approximately equal to d delta y over L. In this case, we're trying to solve for delta y. And so we're going to rearrange this to get L lambda over d. And delta y, I isolate. L is 2.6 meters. Lambda is 656 times 10 to the negative 9, which is 6.56 times 10 to the negative 7. And then we're going to divide all that by 0.0. We have to add 3 zeros. 1, 2, 3, 50 meters. Because this should be in millimeters. Not millimeters, but in meters. 0.1, 2, 3, and then the 0.50 meters. So we add all that in, we sub that in, we do the math, and we get a value of 0.034 meters, which is 3.4 centimeters. And so likewise, from the last one, we would conclude, therefore, the distance between adjacent fringes, or adjacent bright fringes, distance between adjacent bright fringes is 3.4 centimeters. There you go.